Hi, in this segment we're going to learn about fatigue under combined loading, where we have steady loading, alternating loading, and then we would be able to determine the fatigue life even if we have a combination of say torsion and bending and axial load. So in shaft design, as we'll see, we would need to combine the stress due to bending and the stress due to torsion and also some of the axial loads. And some of them may be steady and some may be alternating. So it's now the idea is that how do you combine such types of loads? Before we go there, I want to just discuss the fatigue factors for torsion, and then we will use the distortion energy criterion to combine various stresses from different sources. So if you look here, we see that we have the torsional fatigue strength is given as we have the load factor is 0.59 to convert normal endurance strength to shear endurance strength. And for the ultimate ultimate shear strength, we use also the correlation that the ultimate shear strength is 0.67 of the tensile ultimate strength. Now, if we have a combination of stresses, the combination of stresses would usually come from a variety of sources. Those would be axial and bending and torsional in shaft design. So in each one of those cases, we may have the shaft that would have, say, shoulders, and the shoulders will have fillets that would amplify the nominal stress applied on the shaft. So we must also include the stress concentration factors for each type of loading, as we'll see here. So if we have a combination of loads, then the alternating is given by this long equation that I'll explain in a second, and the mean is given by a very similar equation as you'll see here. So we have two different equations, one for alternating, one for mean. The main idea is that the equivalent stress, sigma prime, is the square root of a bending stress, like or axial stress, would be sigma squared plus 3 tau squared. This is what we learned before. If we have only one stress component in the axial direction or bending direction, and we also have a shear stress component. So this is the von Mises stress in its very simple, in the most simplest case. So the bending or axial stress now is going to be translated, as you can see here, and the shear stress is going to be translated, as you can see here. So the bending or axial stress, we can combine the bending and the axial. The bending would be the stress concentration factor for bending times the actual bending stress plus the stress concentration factor for axial times the axial applied stress divided by the load factor. So we have a load factor 0.85. And then on the other hand, the torsion, the shear stress due to torsion is the stress concentration factor, KFS for torsion, times the shear stress for torsion, tau alternating torsion. So having done that in this equation 655, the mean stress is essentially identical. The only difference is that instead of alternating, we use the symbol M for mean or mid-range stress everywhere. And also the load factor for the axial is not included for the mean. because it is kind of an overkill if we use the load factor for the mean, but when we include it in the axial, it amplifies the alternating stress somewhat, so it is to be on the safe side for alternating stress. So now if we consider now that's the fatigue strength, we would utilize both components for the alternating and the mean. We would use the von Mises stress. And as we have learned, we also need to check for yielding of the combined loading from the first cycle. We could do that simply by saying sigma prime max is less than the sum of the alternating and the mean stress. So this is one way to do it very quickly. But the more rigorous way is that we have to find the maximum stress from the von Mises equivalence maximum stress, which would be the alternating plus the mean, both the axial component or the bending component in this case, and the shear components, as you'll see here. So once we get the maximum stress, then we will check for the stress intensity for the stress concentration factors will be included, and then finally we will obtain the factor of safety for first yield by noting that it is the ratio of the yield strength of the material divided by the maximum stress that we obtain. So this is essentially all what is needed in terms of procedure or theory. So to summarize, we obtain the von Mises stress, and in the von Mises stress we combine bending and axial together with their stress concentration factors, and we combine the shear with its own stress concentration factor. And in case we look for the alternating stress, we would use a load factor for the alternating axial stress, and for the mean we just use straightforward mean values for each of the components that go into the equivalent stress. And that will be essentially, then we essentially can follow a procedure similar to what we've done for just a single component of loading. In addition to that, we have to always guard against yield from the first cycle, and we do that by either finding the maximum stress directly without considering the von Mises, but this is less rigorous, or we can just find the maximum von Mises stress, which is the sum of the mean values and the alternating values for both the bending and for the shear components, and we add them up with the appropriate formula that we've learned here. So next I'm going to discuss, we're going to go through an example, and this example will illustrate a few things. So in this example we will study a shaft, and the shaft is made of a tubing. So the tubing will have an inner diameter and outer diameter, and the tubing has also a drilled hole through it, and the drilled hole is going to amplify all of the stresses that we compute nominally. And we will consider two cases. One case is going to be a case of completely reversed loading with a completely reversed bending and completely reversed torsion. So we have a combination of those two. And then another one where we just have pulsating torque alone. So let's see what, read this together here. So it says that we have rotating shaft is 42 by 4. 42 by 4. This means that this is the OD, and 4 is the thickness of the tubing. So this is how we would read it. We would have an OD and a thickness. When we say 42 by 4, IC 1018, then IC 1018, I know S ultimate for IC 1018, and I can estimate SE directly from S ultimate. So we just can translate as we read. And it has a 6 millimeter diameter hole, so A is equal to 6 when we look for stress concentration factors. And in this case, we want to estimate the factor of safety, guarding against fatigue first, and then second, guarding against static failure. And we would like to do that using Gerber and Langer failure criteria. And we would like to do that for two cases. One is the shaft is subjected to completely reversed torque of 120 Newton meter in phase with a completely reversed bending moment of 150 Newton meter. So we have two things applied at the same time, and they're completely reversed. Completely reversed, it means that the mean value is 0. That's how we translate it. And then the second is different. We have a pulsating torque. It varies from 20 to 160, which means that it has a mean value, and the steady bending moment of 160. So that's kind of a more complex loading situation here. So in our analysis for this example, first thing is we have to estimate SE from SE prime. And in order to do that, we have to go to the table first, A20, find the ultimate strength for IC 1080. That's 440 MPa, and the yield strength of 370, because these are the two numbers we need. The endurance limit will be half of the ultimate, so it'll be 220. And then we start looking at surface factors. Surface factor, if you can see here, and you can see that it is cold drawn. So the surface factor from the table, from the equation, 619, and the table, then we find that it is 4.51 times S ultimate raised to minus 0.265, and that gives us a surface factor of 0.899. Second is the size factor. And the size factor, as you'll see here, it is the tubing diameter divided by 7.62 millimeter raised to this power. We get it to be 0.833. All of the remaining Morin factors, we're going to take them as unity because we don't have any additional information, and therefore we have only 2 out of the Morin factors times 220. Then the fatigue strength went down from SE prime to SE, and SE prime was half of the yield, which is 220. Now SE is 165. All right, so we have now prepared ourselves. We have now all of the data that we require. In essence, we have information on yield because we will use this for the Langer line. We have information on the endurance limit by counting all the factors. Now, the next step in the design process is to do the stress, because now we did the strength. Now we're going to go in and do the stress. And the stress, it depends on the loading. So we have to translate the loading to a stress situation. And that's what we'll do here. First, to prepare ourselves, we have to go and find the ratio of the whole diameter, the whole radius over D, A over D, the whole diameter over D. And that would be 6 millimeter divided by the outside diameter. It would be 0.14. And then the ratio of inner to outer diameter is 0.8. And now we have a table A16 for the stress concentration factors. And from that, we have to use interpolation because the values are in between. So that gives us two factors, one for the bending this is K static or theoretical, 2.366 for bending. And then the other one is K theoretical for shear, 1.75 for torsional shear. Next, I need to translate these stress concentration factors to fatigue stress concentration factors. So I must find the notch sensitivity coefficient Q. So as we learned before, Kf is equal to 1 plus Q times Kt minus 1. We have Kt, but we don't have Q. So we must know Q, and that is a notch sensitivity factor, depends on the notch radius, and we have a figure 620, and that gives us 0.78. So the fatigue stress concentration factor is somewhat smaller. Instead of 2.366, we have 2.07. Same thing we do for the shear, and that changes the stress concentration factor for shear from 1.75 to 1.61. All right, so now we have the stress concentration factors. We need to compute stresses. And when we compute the stress, for bending, I need to find the second moment of area, and I divide it by C. That gives me the sectional modulus, Z. And also for the torsion, I need to find the polar moment of area, which is, if we have like two concentric tubes, one is a tube that has an outer radius or outer diameter and inner diameter, then we can find the polar moment of area as the difference between the outside minus the inside. Having done that, we should be able now to find the bending stress and the torsional stress, as we'll see here. So we got the sectional modulus from the second moment of area divided by half of the diameter, outside diameter. So you have the D down here. And then we also have the second polar moment of area that we have obtained. So this is, it can give us the difference between the outside minus the inside. And therefore we have these numbers. We're able now to compute the stress. So to compute the stress, we have for the alternating bending stress, we have M over Z, and now we have to multiply by Kf, the fatigue stress concentration factor that we computed from before, and we do the computation, we get 93.8 MPa. For the alternating torsional stress, we use the stress concentration factor for shear, and we have the torque times d over 2 divided by j net, which is the difference between outside and inside. That gives us 26.2. And I got now all of the the stresses that I need, the alternating and the shear. So this is axial and this is shear. Both of them are alternating. Then I can now combine them in the von Mises sense, which is taking the square root of sigma axial square plus 3 times the shear square, and therefore the mid-range von Mises stress, the mid-range is 0 obviously because everything is alternating. We don't have any mean value, but the alternating equivalent stress turned out to be 104 MPa. So if you think about this situation, we converted the entire problem into finding an equivalent alternating stress that is equal to 104.2 MPa, and the mean stress is equal to 0. Now we can go and, since we know the strength of the material, S ultimate and S yield and SE, we should be able to construct both the Langer line and the Gerber line if we want, and that looks like this. So we have the Langer line goes from yield to yield. This is the yield is 370, so this point is 370. And the Gerber line goes from SE to S ultimate. So this is the Gerber line. And then the load line for the first part of the problem is going from the origin to the point, operational point, and the operational point is right here. Because we have zero mean, and then we're moving in this direction. So this is basically the operational point. So if I want to compute, for example, the first cycle yield, it will be the ratio of all of this length divided by this length. So this is 370 divided by 105.6. And if I want to compute the fatigue factor of safety, then I have to find this ratio of this length divided by this length, which means that the fatigue factor of safety is 165 divided by 104.2. It gives us 1.58 as the fatigue factor of safety. Okay, so that's kind of a very nice example that we've learned. And now I wanted to continue when we have an alternating component plus a steady component and see that the load line is actually going to change in this case. So let's see the next part of the problem. We'll do it a little bit faster. In this part, we have an alternating torque going from 160 down to 20. So the alternating part is going to be 70, and the mean will be the sum of the two, min and max over 2. We get 90. So we get 70 and 90. And therefore, we are able to compute tau alternating and tau mean, including the stress concentration factors. And we also can compute the steady bending stress component. And from these, we are able to find the von Mises components, sigma alternating and sigma mean. And thus, we have to consider a load point that is as shown here in this example, where the load point is actually right here. So the load line has to pass from the origin through the load point, and this point here has an alternating and a mean, and then we can also now compute the fatigue safety factor as this ratio, and if we want to have the yield, then we have to find the intersection with the Langer line and find the yield safety factor as the ratio of this line divided by this line. So these are given here. So if we're using equations that are in the table, if you remember table 6-7, so the safety factor for fatigue is 3.12 and for yield is 2.93, and that's what you can observe here on the graph, is that the safety factor for fatigue is actually, so fatigue is safety factor is higher than the safety factor for yield, because if you look at the yield, it will be from this point only to the origin divided by the operational value. So here we have already explored the different possibilities for a combination of a steady load and an alternating load. And the steady load can be from bending or torsion, or can be a combination of both. And the way that we treat them now is clear that we use the von Mises criterion, because it's the easiest in combining these types of loading together.